Greetings, physics fans, and welcome to our final lecture on electromagnetic waves. And we're going to finish this by talking about light rays and Snell's law. Right? So previously we've discussed plane waves. We've talked about wavefronts. And we'll draw a picture of it just to remind you, where we'd have our 3D space, X, Y, Z. And you can talk about the electromagnetic waves oscillating down. And we said, well, don't worry about the full picture of the oscillation. Just look for the peak oscillations. And so we've got ourselves just these plane waves propagating this direction at the speed of light. Well, turns out wavefronts come in all sorts of shapes and sizes. Right? If this is what we call a plane wave, we also could have spherical waves. Now, this is going to be my best attempt at a 3D representation. And then we'll cut to 2D slices, and hopefully that'll be a little bit clearer. So, we'll need our 3 axes again. And now let's put a little sphere here. And I'll put a little slice. So we're peering inside this thing. So we'll fill this in. Right? So we have ourselves this glowing ball, basically, radiating outwards, and we're looking inwards. And you could say that there is some sort of light source there that's producing waves. And those waves radiate out in a spherical fashion. And they just keep going radially outwards. Right? Let's go to 2D projections of these. All right. Here are our plane waves again. Oh. This will help us visualize what the heck we're trying to establish. All right, so 2D projections of these wavefronts. What we're going to have is just slice, slice, slice. Propagating that way. Keep going. And boom, we can establish, instead of looking at each plane wave propagating down, just draw a ray going through it. There is a ray of light. That's not very visible. Let's try this in different colors. I'll invert the colors. So I'll make my wavefronts blue. Right. And now I've got rays of light. Ray, wavefront. So the rays are just intersecting the wavefronts and showing the direction the wave is propagating. Do the same thing for the spherical one. Right? Imagine I've got some light source. Could be a star. Could be a light bulb. Right? This thing's radiating in a radial direction. So here are my wavefronts. Spherically outwards. And what rays are being radiated by this star? Well, the rays are 2. So, what we've done now is say these electromagnetic waves, it's this crazy complex picture of electric fields oscillating, generating magnetic fields that are oscillating. And then we said, okay, let's talk about the wavefronts. And you say, find the phase of these things. And finally, we're going to reduce this down to a nice simple picture. We're going to focus on those rays. And we say, well, what is the path of this light as it propagates? Where is this going? So, let's talk about some ray properties, right? One thing you should notice here, the rays are going to always be perpendicular to wavefronts. Always make a 90-degree angle. Right. So this should remind you of the equipotential lines. And that is not by coincidence. Equipotential lines and the electric fields going orthogonally through them. So what we're going to do is use rays now to describe a specific set of problems called geometric optics. So let's start defining new sets of problems that we're going to tackle. And the first thing we have to say, we need to establish what are our rays traveling through. So our waves are going to travel through some kind of medium, right? And that's going to be whatever material the rays are traveling through. So, some examples. You could be vacuum. Electromagnetic waves, they have no problem getting through the vacuum of space. Sound, different story, it can't get there. But we know light rays can travel through air. You can see me right now, and there's probably a pocket of air between your monitor and your eyeball. That light's traveling through some glass. Heck, why do people love diamonds? Because of their optical properties, the way they change, refract the light, and so on, all right? There are tons of different types of mediums out there. And now, critical stuff. This is going to be what we're focused on now. When a ray, let's make that, when it transitions, right, or it moves between mediums, two things will happen. All right, number one, some of that ray will be reflected. And then some of the ray is refracted. So we're going to have reflections and refractions. Let's draw a little picture of this. I'm going to get myself a little pane of glass. So here's my glass. And I'm going to shoot a ray into this. And I want to be careful, so I'm going to use a nice ruler here. And I'm going to have my ray come in at some angle. Arbitrary for now, we'll start signing. But here's my incoming ray, and it hits that medium. Some of it's reflected. Well, that's easy. The reflected part just bounces off at that same angle. So we have a reflected. This is what we'll call our incident. And then some of it is refracted. So instead of going straight through, let's see here, it's going to bend. The light will bend. Let's go for a little bit more extreme. The light refracts, changes path. So here's our refracted ray. All right. Well, we're going to start assigning angles to all of these. So to assign angles, angles are measured, let's see, with respect to the normal. By normal, I'd say, here's my plane of incidence, here's my normal line. The normal line. So here's my incident angle, I'll call it theta I. And there's my refracted angle, call it theta R. All right. So important. We're always going to measure angles with respect to the normal line. So let's do this in a little bit more detail. All right. Let's do reflections. They're a little bit easier. Let's bring my nice handy ruler back in. So I've got some mirror. And a ray is going to come in. So I'll come in nice 30 degrees. Come on. There we go. So, well, the ray, it comes in. Here's our normal. I'm going to keep using the straight edge a lot today. All right. So, this incoming ray, measure respect to this normal, sees a 60-degree angle from the one I've drawn. Then the reflected ray, you already know this, you can visualize it. You know that's going to bounce off at that same angle. So it has to reflect the same way. There's my reflected ray, also at 60 degrees. All right. So when we're talking about reflections, the incident and reflected angle are always the same. And that's important enough that it gets its own little box. Right. So reflections, that's easy. Now we gotta do refractions. That's gonna take some work. All right. So, ways to think about this. It is a bending of a ray when it moves to a new medium. Right. For those of you who think about your glass of water. Right. Get your glass of water here. Let's fill this up. Right. And then you put in your straw. And what do you notice? You put your straw into the glass, and suddenly it looks broken or twisted or kinked. Right? That's an example of refraction. It's the bending of the rays as it transits from water to air versus above. It's the light refracting as it transitions between mediums. All right? So that bending is caused by changes in speed. Yes, it turns out the speed of light does change depending on what you're moving through. So, to get an idea, right, what's going on here, think about how fast you run, right? Imagine how fast you can run in an open field. All right, so you're doing your dead sprints, you're moving as fast as you possibly can. Now, compare that your top speed in a crowded hallway. Or a pool of water. Right? Your speed is medium dependent. And it's the same thing for water. Or same thing for light. So, definition now. We're going to define our index of refraction. This is an optical property. Index fraction. It is a lowercase n, and it's defined as the speed of light over the velocity, or the speed of light, in medium. So, big, important definition here, guys. Right? So this n value just says what is the speed of light versus how fast that light can move when it's in medium. So light slows down when it hits the air. It slows down more when it hits the water. All right. So let's list some values. First things I want to say is that n is always going to be a number greater than or equal to 1. If the medium is vacuum, n is 1. Anything higher, anything of a greater index of refraction slows down the light. So let's give some list examples, median and the corresponding index. So like I said, if you are a vacuum, the index is just 1. If you're in water, the index, let's go back. Let's do air first. If you're in air is about 1.0003. So we're going to call that about 1. For all the purposes in this course, we'll say the index refraction of air is 1. It's a little bit more than that, but close enough. We could say water, which we'll say is 1.333. Glass. How much does glass bend the light? Well, depends on the type of glass you use. It's anywhere between 1.5 to 1.6 for most types of glasses that we see. And diamonds. Let's go to the higher end now. Diamonds. known for their brilliance, how they reflect and refract the light around. For our purposes, we'll say a diamond has a nominal value of 2.4. So there's a range of values for that index, one being the absolute minimum and just ever increasing depending on the material. And it's a material property. I change mediums, I change in. Plain and simple. So we established that when I'm moving through a medium, my speed changes. Well, now we need to say, hey, we started off with that straw in the glass, and you saw how much you saw the straw bending. So let's talk about how much it bends. All right, the amount of refraction. All right, that is given by what's called Snell's law.